Let's learn how to solve dynamic equilibrium problems. Here's a list of some forces you need to know. If you're not familiar with them, please pause the video and write them down. Here are the steps we would use to solve these second law problems. Again, if you're not familiar with these steps, please pause the video and write them down. An object is in dynamic equilibrium if, first of all, the sum of the forces on the object add up to 0. So in one dimension, Newton's second law would look like that. In 2 dimensions, Newton's second law would look like this, where the forces in the horizontal equal 0 and the forces in the vertical equal 0. Specifically, an object is in dynamic equilibrium if the velocity is a non-zero constant. In other words, an object is in dynamic equilibrium if the object is moving with constant velocity, and that velocity is not zero. So a motion map would look like this, where the object has constant velocity, in this case to the right, but the acceleration is 0, or it could be moving in the opposite direction. Compare this to static equilibrium, where the object is not moving at all. But in dynamic equilibrium, the object is moving, but with constant velocity. Here's the dynamic equilibrium example that we will solve. The box in this picture is pulled with constant velocity. That's a key part of this problem. We need to find the force that the surface applies to the box. Normally that's called the normal force. And we want to find the force of friction. Because this object is moving, that's going to be a kinetic frictional force. First of all, we want to identify the system that's being accelerated. In this case, it is the block. We want to define the coordinate system. We'll say upward is positive and to the right is positive. We want to draw a force diagram and a motion map. So the force diagram will look like this. The surface is pushing the block upward. The force due to gravity is pulling down on the block. The string is pulling it at an angle with a force of tension up and to the right. And there is some kinetic frictional force pulling the block to the left. The object moves with constant velocity along the surface horizontally to the right. So the velocity is constant, and because the velocity is constant, the acceleration is 0. So step 3, we ask ourselves, are there any forces that are off axis? In this case, there is. The force of tension is a force, and the only force that is off axis. So we have to draw in the horizontal component of the force of tension and the vertical component of the force of tension. Do we need to rotate this? Well, in this case, the answer is no, because rotating this particular force diagram does not help us. Then we explicitly write out the sum of the forces equals mass times acceleration to get credit. Then we write the second law equations in the horizontal and the vertical. So let's look at the horizontal first. So we write out Newton's second law in the horizontal, which looks like that. The sum of the forces in the x equals the mass times acceleration in the x. And we identify just the horizontal forces. The horizontal forces are Ftx and Fk. So we add those up just like Newton's second law says to do, and we set that sum equal to the mass times acceleration of the block in the horizontal direction. But because the accelerations are 0, we know that this product of the mass and the acceleration in the horizontal will also equal 0. In the vertical, we also write out Newton's second law, where we add up all the forces in the vertical. In this case, there's the normal force, the vertical component of the force of tension and the force due to gravity. We add those up just like Newton's second law says to do, add up all the forces in the vertical, set them equal to the mass times the acceleration in the vertical. Again, this object's not moving, let alone moving in the vertical, so since the vertical acceleration is 0, the product of the mass times acceleration in the vertical will also be 0. Now, let's look at this right triangle specifically. That includes the force of tension as the hypotenuse of the right triangle, and FTY as being the vertical leg and FTX as being the horizontal leg. Let's look at that in more detail in this picture in the middle. So we know, because the problem told us that the force of tension is 100 newtons. This angle was given to us as 30 degrees. So we can use SOHCAHTOA to figure out the two other legs, FTY and FTX. Because FTY is opposite from the angle, we can use the sine function to solve for FTY. So that would be 100 newtons times the sine of 30 degrees. That gives us a value of a positive 50 newtons, and it's positive because my force of tension in the vertical is pointing upward. That component of the force of tension is pointing upward. Then for FTX, notice that's in the horizontal, and it's adjacent to this 30 degrees. So we will use the cosine function. 100 times the cosine of 30 degrees. That gives us 86.6 newtons, and again, it's positive because it's pointing to the right. So we have FTY and FTX. Another thing that we need to solve for is FG. FG is pointing straight down. We haven't rotated it, so it's pointing straight down. So we leave the negative sign in for the negative 9.8 newtons per kilogram. This could be meters per second squared too, depending on which set of units you want to use. We multiply that times the mass, because remember our equation for the force due to gravity is acceleration due to gravity times the mass, and we get a value of negative 490 newtons. Negative sign is very important here because it's the force due to gravity is pointing downward. So let's look at the horizontal. In the horizontal, we said that this is our equation, our Newton's second law equation in the horizontal. We solve for FTX as being a positive 86.6 newtons. So there's our substitution of positive 86.6 newtons plus the kinetic frictional force equaling 0. So solving this problem gives us a kinetic frictional force of negative 86.6 newtons. We know the negative sign has got to be correct because our kinetic frictional force is pointing to the left. Then now let's look at the vertical. In the vertical, we decided that, or we calculated that this is our Newton's second law equation in the vertical direction. Now, we're looking for the normal force, so that's our unknown. FTY we solved to be a positive 50 newtons, so we substitute that in for our equation. And FG is a negative 490 newtons, so we plug that in as negative 490 newtons. And our normal force, or the force that the surface applies to the block, is 440 newtons. And that's how we solve at least one example of dynamic equilibrium.